To engineer modern materials, like targeted pharmaceutical drugs, next-generation OLED screens, or advanced battery electrolytes, we have to build them atom by atom. But before synthesizing anything in a lab, researchers need to predict exactly how complex molecules will interact, fold, and bond in a digital environment. These interactions are governed by the strict rules of physics, specifically the quantum behavior of atomic nuclei and their surrounding electron clouds. To build a perfectly accurate digital twin of any material, you theoretically need to simulate it using full, uncompromised quantum mechanics. The materials of tomorrow rely entirely on our ability to compute the quantum mechanics of today, and that presents an immediate, catastrophic computational problem. Calculating full quantum mechanics means solving the exact electronic Schrödinger equation for every single particle in your system. You have to track the exact mathematical position of every nucleus and every single electron simultaneously. You also have to continuously calculate their vibrations, polarizations, quantum spin, and constant electron correlation at every instant. For anything larger than a handful of atoms, this computation becomes mathematically impossible. As this diagram details, tracking full quantum mechanics for large systems, like an entire folded protein, forces the computer into an infinite processing loop. We simply cannot explicitly track every electron to simulate everyday materials. Because the math is too complex for large systems, we have to bypass the quantum bottleneck entirely. We do this by inventing a master abstraction layer. This diagram shows how we solve the problem. Instead of trying to track the entire chaotic quantum wave of every electron, we simplify the wave into a single classical curve. That resulting curve is called an effective potential. An effective potential is a mathematical model that summarizes the total push and pull between molecules into one useful energy curve, based entirely on the physical distance between them. This leads us to the most famous and widely used of these models, the Lennard-Jones potential formula. This equation is not exact quantum mechanics. It is a highly practical approximation designed for speed and scale. Looking at the math, the formula relies on two competing terms. One dictates short-range repulsion, pushing molecules apart, and the other calculates long-range attraction, pulling them together. These effective potentials act as a universal translator. They take the impossibly complex quantum language of electrons and convert it into a practical force field we can actually run on a computer. Let's break down this curve, starting with this steep upward line in zone 1. This illustrates what happens when two molecules are forced dangerously close together. The physical cause of this energy spike is shown here. When molecules approach each other, their individual electron clouds overlap too strongly. This triggers a strict rule of physics, the Pauli exclusion principle. Because electrons are fermions, this principle dictates that two electrons cannot occupy the exact same quantum state simultaneously. To avoid sharing a state, the system reacts violently. It is forced to rearrange into significantly higher energy arrangements, creating extreme short-range exchange repulsion. In our formula, this extreme repulsion is represented by the highly sensitive, steeply curving 12th power term. That single mathematical term simulates the invisible quantum wall that gives solid objects their physical volume and stops ordinary matter from collapsing in on itself. Now we move to the second half of the interaction, how molecules behave at a distance, mapped here in zone 3. Charged ions and polar molecules obviously attract each other through basic electrostatics, but even perfectly neutral atoms, like noble gases, exert a pull on each other. This chart identifies the quantum origin of this pull. It's called dispersion, or London forces. Even in neutral atoms, quantum fluctuations in the electron cloud create temporary, shifting dipoles. These instantly induce matching dipoles in neighboring atoms, pulling them together. In our equation, this weak long-range attraction is represented by the 6th power term. By plotting both terms together, we find a critical balance point. Look at the lowest dip in zone 2. This is the exact physical distance where the strong repulsion and weak attraction cancel out, creating a stable energy minimum. Simulation software utilizes this completed curve by applying a straightforward rule. Physical force is calculated as the negative gradient of potential energy. With this equation, computers don't need to track electron waves. They simply move particles mathematically in whichever direction lowers their potential energy, mimicking physical reality perfectly. Modeling two atoms is just the baseline. To engineer true materials, we have to scale this logic up to encompass billions of interacting particles simultaneously. The framework required to manage this immense scale is statistical mechanics. At massive scales, a new, competing variable must be introduced into the simulation: temperature. This represents chaotic thermal motion. The bulk properties of any material emerge from a continuous battle between that thermal motion and the attractions defined by our effective potential curves. This diagram outlines the outcomes. If thermal motion overpowers weak attractions, molecules tear apart, seen in the gas container on the left. Conversely, if attraction dominates thermal heat, particles lock into rigid geometric grids, yielding the solid container on the right. Statistical mechanics proves that the macro phases of matter are just the statistical averages of billions of particles navigating their potential energy curves. We can now connect specific shapes of these microscopic energy curves directly to everyday tangible physical properties. Look at the top row. A deep energy minimum translates directly to a high boiling point. Immense thermal energy is required to escape that well. Dropping down, extensive hydrogen bonding manifests as intense surface tension and fluid viscosity, resisting sliding. This bottom panel addresses a common misconception. Everyday macroscopic behaviors in biology and materials are direct descendants of quantum-level interactions. The entire workflow of modern material science is mapped here. We start with the extreme complexity of overlapping electron clouds, calculate the math of dispersion and repulsion, and abstract them into effective potentials. Mastering these potentials is exactly what currently drives advancements in targeted pharmaceutical binding, custom nanotech polymers, and safer advanced battery electrolytes. By bypassing reality's quantum source code and mathematically abstracting the invisible forces of matter, we transition from merely observing the physical world to actively engineering it.